Welcome back for your next Algebra 2 lesson. So here we're moving on to section 1-2, and what we're going to be talking about is the properties of real numbers. And again, if you notice, our learning targets for today, what I want you to take away from this is you're going to be able to graph and order real numbers after this lesson, and you're going to be able to identify properties of real numbers. So to begin, let's talk about classifications or the subset of numbers. Okay, so there are a lot of different numbers in the world, okay? And so we as mathematicians have partitioned them. We've made subsets of numbers to help describe the types of numbers we're talking about. Now, I think about way back thousands of years ago when math first started. What we were talking about was things that they could count, things that they could see in the real world. So if they're looking for food, you could see 1 apple, 2 apples, 3 apples, 4 apples. They would only be able to see things that they could physically count in the world. And we call those the natural numbers. The natural numbers are our counting numbers. But after that, math began to evolve, okay? People began to realize the idea of having nothing, okay? That the lack of something is called zero, just not being there. Once they introduced zero, you still had all the counting numbers with it, but now you can see you have zero as well. And when you include zero in that list of numbers, what you're now talking about are the whole numbers. So the whole numbers again is zero and all of the counting numbers. But then math began to evolve even beyond that. They got the idea of negative, okay? So think about negative. So when banks came around, I mean, obviously you like when you have money, but they also have to represent what happened if you owed money, if you had negative money. So that's where the negatives start coming in. You can see that reflected in this next grouping. Once those came around, we began to call those the integers. So the integers are the counting numbers, their opposites, and zero. And then it kept evolving even beyond that. What if you had half of something? What if you had a third of something? Not everything can be physically counted in wholes. So there we started talking about the rational numbers. Okay? Now, rational numbers have some special unique traits, okay? So again, we're talking about this group right there. Now let's describe what makes a rational number. This is one of the more interesting subsets that we get to talk about. So rational numbers are all numbers that you can write as a quotient of two integers. So a divided by b. So two integers dividing, as long as, again, you can't divide by zero. We all know you can't do that. What's another qualification? So this also includes what we call terminating decimals. Because if you think about the number 0.125, it can be written as 1/8. If you think about the number 0.5, it can be written as 1/2. So any terminating decimal that has an n that you can see, that is going to be, again, a rational number. And finally, it includes repeating decimals. So for example, 0.3 repeating. 0.3 repeating can be represented by 1/3. Therefore, it also counts as a rational number. So those are the three classifications of numbers to be qualified as rational. Well then it even got a little bit more complicated than that. Math continued to evolve, and we got numbers such as these: 1/2, pi, things like that, things that were not a terminating decimal, they had no end, and they can't be written as a fraction. So how do we qualify those? Well, irrational numbers have decimal representations that neither terminate nor repeat. So for example, if you type square root of 2 into your calculator, you're going to get 1.41423 dot dot dot. It's just going to keep going. I call this number vomit. Okay, your calculator just spits it out at you. It never ends, never repeats. Those are the irrational numbers. All right, so again, cannot be written as quotients of integers. So that's kind of the world of real numbers that we talk about. Now, it's important that we can classify where numbers belong. Okay, so let's think about this. the number of people participating in a race. We need to decide what category of number, what subset of number does that belong to? But let's think about how many people can participate. Well, you could have no one, okay, empty race. You could have one, you could have two people, you could have three people, so on and so forth. Now, I think we can agree it doesn't really make sense to have negative people in a race, right? You can't include negative people. You can't include halves of people. You can't have 1.5 people participating in the race. So think about what qualifies 0, 1, 2, 3, so on and so forth. And I think you can see in the red there, that's going to qualify it as a whole number. Okay, so that first one is going to be a whole number. All right, how about the time it takes to drive to school? All right, so time it takes to drive to school. All right, now, would it make sense for negative time to drive to school? Not really. So we're talking about positive values. Could it take you no time? Well, we're not going to say that you're living at school, okay? We're going to say that you're outside of that realm, okay? You're not at school, so we're going to be talking about something certainly positive, all right? So only positive values. So not including 0, only positive. Well, that only has one thing that would work. 1, 2, 3, so on and so forth, okay? Because you only want the positives. The amount of money in your bank account. All right, so the amount of money that you can have in your bank. Can you have positive money? Well, naturally. Can you have negative money? Can you go into debt? The answer is yes. That's where people start getting themselves into trouble if they have negative money left. If they spend more than they have negative money. Okay? Now, can you also have parts? Do you have to have whole dollar increments? No, you can have $1.26, you can have $101.50. So, for the amount of money in your bank account, you're not talking about having to be whole numbers. You want to include the negatives. So to me, that's going to be focusing in the green there. That's going to be rational, all right? So rational numbers will represent the type of amounts of money that you can have in your bank account. So there's some practice describing types of numbers. Now, once we understand types of numbers, we start to have a conversation about comparing numbers. Now, the easiest way to compare numbers, the easiest way to do that is if you look at their decimal form. All right, so for example, trying to talk about the square root of 3. Well, ultimately, we may not know what that is. So it's a lot easier for us if we look at the decimal representation. So if you just type square root of 3 into your calculator, you will get 1.73. Now, this would be a fantastic time to have your calculator in front of you. Make sure you know where the square root button is, because I guarantee you in the practice work for class, on the test down the road, you are going to have to be able to do this. So make sure you know right now that you know where that square root button is on the calculator so you can make these comparisons. All right, so we want to graph the following numbers on each number line. All right, so -5/2. I know this off the top of my head. If you don't, feel free, type it into the calculator, okay? Don't be embarrassed to use it. You type in -5/2, you get -2.5. You type in the square root of 1/2, or the square root of 2. You get a little over 1.41, and then 2.6 repeating. We're going to round off to 2.66. Technically, that should be 2.67, but for the intents and purposes of just putting on a number line, that is going to be fine. All right, so now let's start putting these on. Negative 2.5. So negative 2.5 is in between negative 2 and negative 3. So remember, when you're dealing with the opposites, you're working leftward, okay? So negatives, the more negative you are, the more left you are. So negative 2.5 is in between negative 2 and negative 3. So I'm going to label that as my negative 5 halves. Square root of 2, we said it was 1.41. So it's going to be a little bit less than 1.5. And then 2.6 repeating is a little bit over 2.5. And that's how you can put them on a number line. All right, let's do another quick one to practice. So again, any number that is not in decimal form, you want to put in decimal form. So that square root of 3, I'm going to call 1.73. 1.4 repeating, we're going to round off to 1.44. 1/3, we're going to call 0.33. All right, 1.73. So 1.73 is going to be in between 1.5 and 2. So I'll call that square root of 3. 1.44 is going to be in between 1 and 1.5, 1.5. So I'll put myself right there. Then 1/3 is less than 0.5. So I will go like that and call that 1/3. All right, so do familiarize yourself with making sure that you can put those on a number line. We can also do straight up comparisons with these. So to do straight up comparisons, same deal. So I'm going to type square root of 17 into my calculator. So I get 4.12, and I'm comparing it to 3.8. And again, big picture here, when you're dealing with inequalities, it's going to open towards the larger number. So here, clearly the larger number is the 4.12. So to compare these, I would have my inequality opening towards the larger one. But again, that would be difficult to see if you didn't put it in decimal form. Next one, same thing. I'm going to put negative square root of 26 in my calculator. That's going to give me negative negative 5.10 when I round it off, compared to negative 6.25. All right, now, tricky thing here. Both of these numbers are negative, okay? And so you have to think the greater one, when you're dealing with two negatives, the greater one is the one that's closer to 0. The one that's closer to 0 is at negative 5.10. Okay, so that one's a little bit tricky. I've seen kids mess this up. When dealing with two negative numbers, again, it's a little bit awkward because the one that looks like the lesser of the two is actually greater because it's the one closer to 0, the one closer to the right. So please make sure you keep that straight because it's very easy to make simple mistakes on that concept. Moving right along. So we've talked about comparing and graphing real numbers. Now we're going to talk about the properties of numbers. So for example, the opposite or additive inverse of any number is the negative of that number. So for example, the opposite or the additive inverse of 12 is negative 12. The opposite or additive inverse of negative 7 is 7. When you add the two additive opposites together, you're going to get 0. All right, the reciprocal or the multiplicative inverse is 1 over that number. And again, you know that as the reciprocal, but essentially what the property is something multiplied with its reciprocal is going to give you 1. All right, so 8 times 1/8 -5 times -1/5. When you multiply a number with its multiplicative inverse, you're going to get 1. Okay? So let's run through some of these properties. The closure property. All the closure property means is if A is a real number and B is a real number, then A plus B is a real number and A times B is a real number, okay? That's called the closure, that the two numbers you start with are in the same set as the answer. So again, if you start with real numbers, you end with real numbers. Commutative. The commutative property. Commutative deals with order. All right, so I'm even going to write that right here. Commutative deals with order. So what I mean by that is A plus B is the same as B plus A. A times B is the same thing as B times A. Again, the order doesn't matter. They're going to be equivalent. They're going to be the same thing, okay? That's the commutative property. Associative property. The associative property is a little bit different. Associative property means grouping doesn't matter. So what that means is if you're adding three numbers together, it doesn't matter if you do A plus B first and then add C, or if you add B and C together and add it to A, or vice versa. Same thing works with multiplication. So grouping. Now, these two are really easy to forget. They're obvious properties, but it's easy to forget which means which. Okay, so the idea here to help you remember is associative. Associate. Who do you associate with? Well, the people you associate with, you often find in a group, right? Your group of friends, your family group, anything like that. So association deals with grouping, all right? So if you can remember that, then you can remember that commutative is the other one. Commutative is the order. But again, I think associative is easy to remember. If you think, who do I associate with? I associate with my group, okay? Group of friends, group of family, however you want to consider that. Next is the identity. Now, what identity means is that whatever you're doing doesn't change the number you started with. So with addition, the identity is 0, because if you add 0 to a number, it doesn't change it. The identity for multiplication is 1, because if you multiply anything by 1, again, it doesn't change it. Inverses, we just talked about, the additive inverse, or the opposite, the multiplicative inverse, or the reciprocal, and then the distributive property, the famous one you've seen for years, where you distribute A to both B and C. All right, so there's a little review of what these properties are. So now let's go through some examples. All right, so which property does the equation -2/3 times -3/2 equals 1? What property does that illustrate? So it's illustrating two things multiplying to become 1. And so first of all, you're multiplying something by its reciprocal. So we're talking about the inverse. Okay, inverse. Now, I would like you to be more specific. What type of inverse? Because remember, there's two of them. It is the multiplicative inverse. Again, and that should be obvious, you're multiplying, but again, inverse, you're thinking multiplying two things together to give you 1. That is a multiplicative inverse. What about the next one? 3 times 4, and then multiplying by 5, or 4 times 3, and then multiplying by 5. So here, don't be deceived, because here I see some grouping happening, right? There are groups formed, but the group isn't the thing that's changing. What's changing? Well, what's changing here is the order. 3 times 4, 4 times 3. So when the order changes, but it stays the same, remember order is commutative. So the commutative property. And then finally, the last one, which property does that equation represent? So again, I see some grouping happening, but the interesting thing is it's not the grouping that's changing. What's changing here? Well, they're taking that 3 and they multiplied it into the parenthesis. And remember, that has a really special name, something that's been drilled into you since exponential algebra. That is the distributive property right there. All right, last page, and then you'll be good to go. So let's run through a couple more just to make sure that you're feeling comfortable with this and getting this. All right, so XYZ is the same thing as XZY. What I'm noticing is the order is changing, right? You flip the X and the Y and the Z, but it stays the same. When order changes, that is the commutative property. What about B, where the group is changing? The first one, you're multiplying F and G and then H, or then F and then G times H. When grouping changes, you're talking about the associative property. All right, in C, so C, notice there is grouping, but it's not the grouping that's changing. What's changing in C? Well, I'm noticing P plus Q, but then here is Q plus P. You flipped the order, okay? The order changed. So because the order changed, that makes it commutative. In D, I notice that I'm multiplying by something and it's not changing the value. I started with 5, multiplied by the 1, and it stayed 5. Remember, whenever you do something and it doesn't change. So here, no change. When the value doesn't change, you're talking about the identity. All right, the identity means absolutely zero change. In this one, you're adding to give yourself 0. So you're adding something and its opposite, and it becomes 0. And remember, that is the inverse, okay? And again, it's always a good idea to label what type. So this is the inverse of addition. And then in F, what's happening? V plus 0 plus W equals V plus W. Well, I notice I'm adding 0 in there, and there's no change, right? Adding 0 doesn't change anything. And again, that no change idea is representing what the identity of it is. The identity of addition is adding 0, all right? All right, so that is going to be it for our notes. So what I'd like you to do is, after our first notes, I modeled how to write an appropriate summary. So now I want you to try, okay? So here, take a few minutes at the end of this video, and I want you to summarize something you learned. Or you could write me some questions, something you're still wondering about after watching this video. But the goal here is just to reflect. Reflect on what you learned, or reflect on what you would still like to know. So I'd like you to take a moment, do that for me, and then we will work on our practice work in class.